Welcome to August 19th LeetCode Challenge, maximum product of a split binary tree. Given the root of a binary tree, split the binary tree into two subtrees by removing one of its edges, one edge such that the product of the sums of the subtree is maximized. Return the maximum product of the sums of two subtrees. Since the answers may be too large, return the modulo of 10 to the 9 plus 7. Note that you need to maximize the answer before taking the modulus, not taking it after. So basically, here, give an example. If we have a binary tree here called root, and if we remove the red branch right here, we have the sum of this entire binary tree to be 11, and the sum of the remaining binary tree to be of the branch should be 10. And you multiply 10 times 11, which gets you 110, which is probably the largest maximum number you can get from the split. Likewise, you're given this binary tree example here. You will split the branch where the red is right here between 2 and 4. And then you get the sum of 6 times 15, which gives you 90. And pretty much you want to split the tree where you could find the maximum number of the product between the sums of the sums. So let's look at the hint here. So yeah, keep the max total of the sum of the tree minus the subtree times the subtree of each node. That makes perfect sense. Let's do something quite similar to that. So in order to kind of assess and know which node we're going to branch at, we need to be able to search through each node of the tree. And I think the best approach would be to use a depth first search, and we're going to search through the tree basically and find the current sum. So basically we're going to loop through each of the node of each tree, and then we're going to add the sum. Right? We loop through 1, add the sum, which is 1. Loop through here, add the sum. If we cut the branch here, it will be cut the branch here, it will be 1. Cut the branch here, it will be whatever the remaining is times 3. Cut the branch here, it will be 6 times 15. Cut the branch here, it will be 5 times the rest. Cut the branch here, it will be 6 times the rest. So we want to do the depth first search. So let's define a function here, depth first search, DSF, and we're going to take in the root. Next, we need to know if the root itself is equal to none, then we could return 0 because there's nothing to return. So we are going to update the current sum. So cur sum, or let's see what the notation they use here. Subtree sum, that's too long. I'm going to use current sum. Current sum is going to be a recursive function. So depth first search is recursive of the root dot left using the tree node class here. Left plus depth first search of root dot right. So, and then plus the root dot value itself. That's the thing we want to add together. And then we're gonna develop an answer here. So we're gonna self dot output. Output would be the maximum of, what does it say here? Maximum, let's copy something similar to that. Maximum between self dot output and current sum times self dot total sum minus current sum. Then we want to return the current sum. So that's our depth first search algorithm. Next thing we need to do is run the actual algorithm of max product. So what we're going to do is assign self.output to be 0. We want self.total sum to be 0. Next thing we'll do is basically run the depth first search algorithm. Self.total sum will be assigned to depth first search of the root. Firstly, get the total sum of all the nodes in the binary tree. Then we want to run the depth first search. Then we want to run the depth first search in post order in order to calculate the sum of each subtree and its complement. And then we return self.output. And we want that to take the modulus between 10 to the 9 plus 7. Let's run that. Oh, what am I doing? Root.write. Cursum, total sum. Alright, looks similar. Let's submit it. Accepted. Awesome. Let's see. So basically what we do is remove any edge of the binary tree. We can form a subtree and its complement. Basically, this is the subtree and its complement. Firstly, what we'll do is we ran a depth first search to calculate the total sum of all nodes in the binary tree. Then we ran a depth first search in post order here to calculate the sum of each subtree in the binary tree. Pretty much, if the sum of the current subtree is current sum, and this complement is total sum minus current sum, we update the answer or the output to be the max between the output and the current sum times the total sum, the complement. Space time complexity is big O of n, where n is the number of nodes in the binary tree. Space complexity is big O of height, or h, which is the height at the binary tree. So how deep does it go? Which has to do with this, which gets accounted for the stack depth of the recursion, right? Because we do it recursively. So basically, best case scenario would be big O of log n, and worst case is big O of n, right? So it'd be a big O of the height of the tree for space complexity. So yeah, that's pretty much it. Have a great day, guys.